In this video, we are going to talk about solubility and concentration. Specifically, I'm going to introduce the concept of solubility, discuss how we know what compounds will dissolve in what solvents, and discuss the vocabulary surrounding solubility before giving examples of some common concentration units. So first, a little bit of vocabulary review. Remember that we have a homogeneous mixture, and that is something that is a combination of two or more compounds, and it is uniform throughout. And so what we call this is a solution. So a solution is just some compound that has something else dissolved in it. And if we were to look at a test tube and see a solution that's uniform throughout, that's the solution. And then sometimes we will see a little bit of solid at the bottom, and this is the precipitate or precipitate. This undissolved solid can come from there being too much solid in the test tube, or it can come from a chemical reaction happening. So as an example here, normal saline solution. So this is what's in the big IV bags in medical settings, and often things are injected into it to flow through the IV. Normal saline solution is 9 grams of sodium chloride dissolved in 1 liter of water. So in this situation, the sodium chloride, the NaCl, that is the solute, and then water is the solvent, and the whole thing is the normal saline solution. So in this course, we're mostly going to be concerned with things that are in a liquid solution. There are others, but these are really the most important, and we will often talk about liquids. And when we do our labs, we're pretty much using a liquid solution, and it comes from a liquid solvent, and there is often a solid or a liquid dissolved in it. So you don't need to be able to talk about all of these, but just be aware that you can have a solution that's really any sort of phase. So how do we know if something will dissolve? Well, we have to think about the intermolecular forces. Now, this is something that we're not going to spend much time on. You don't need to be able to describe all of them, but I do want us to think about how something is interacting with the compounds and particles around it. So we've talked about gases and how they interact with the walls of a container. Now we can also think about the water molecules interacting with each other, and we can think about the solute molecule and or the solute ion or atom, and if that's going to interact with the solvent particles. So really the key is this shortcut of like dissolves like. So meaning that if you have something that is polar or charged, it will dissolve in a polar solvent, and water is the most common of the polar solvents. Solvents that are nonpolar will mostly dissolve in nonpolar solutes. And so we've seen this in things like oil and vinegar. Oil and vinegar don't mix because you have a nonpolar and a polar compound or solution, and it's really hard to get those to mix because they just don't have favorable interactions with each other. So the intermolecular forces don't help them interact. And so we don't need to know what those are to understand that they aren't favorable. And so the shortcut you can use is polar dissolves polar and ionic, and nonpolar dissolves nonpolar. So let's talk a little bit about what those intra versus intermolecular forces are. So the intra, those are the inside ones, and so these are the covalent bonds. And covalent bonds do not get broken by things like boiling water on your stove. And so when we think about the phase change water lab, we have a water molecule, and it looks like this, and these are the covalent bonds, and these do not break. So when you boil water, what you're actually doing is disrupting the interaction between two different water molecules, which is what the intermolecular forces are. And these are weaker. So this is what's disrupted upon a phase change. And we see that the phase, remember, is changing a phase is a physical change. We're not changing the chemical makeup of the compound. And so we can't break a covalent bond and have individual atoms because that would be a chemical change. And so if you ever forget which one is which, just remember that you can't change the compound itself when it's a physical change. Changing phase is physical change. And so you're not breaking any of these bonds here. You're only disrupting the interactions between two molecules. And so one thing that we need to think about is bond polarity. So how do we know if something is polar or nonpolar? So electrons in a covalent bond are not always shared equally. We talked about this a little bit when we did the molecular modeling and the three-dimensional shapes. So electronegativity is the vocabulary word, and that is the thing that describes how strongly atoms attract electrons when they are in a bond. And so we have atoms that are not generally all that electronegative. They don't tend to pull electrons towards themselves, they tend to release electrons. Unsurprisingly, the least electronegative atoms are those that form cations, and the most electronegative are those that form anions. And the polar covalent bond can form when you have an uneven sharing of electrons. So here, a nonpolar covalent bond, we have two of the exact same atom. So the electrons aren't going to feel a bigger pull towards either side. But if you have something where the one on one side is much more electronegative, meaning electrons are being pulled this way, this means that this side is going to have what we would call a partial negative charge, and this would have a partial positive charge. So the electrons are being pulled in this direction. So you can think of this arrow as the electrons being pulled toward the chloride here, and the hydrogen is going to be have less or fewer negative charge. So remember that in a bond, electrons are constantly moving around, and this would mean that most of the time the greater negative charge is over here by the chlorine than it is by the hydrogen. And so we can look at this scale here, and this tells us how we know if a bond is going to be covalent, just pure covalent, if it's going to be a polar covalent bond, or if it's an ionic bond. So one thing to note here is this is about, this is like kind of approximate. And so what we're going to use in this class, I mean, you can look at this number, you will be given this chart, so you can always use that. But the real way to tell if something is ionic is we're going to just use if it's a metal and a nonmetal, because the ionic compounds that we see in this course have the metal and the nonmetal together. So we're going to use that as our definition for ionic. And then all you need to know then is a nonpolar covalent bond, you have to have a difference in electronegativity that is 0.4 or less than 0.4. So one example of that would be if we look at our carbon here and our hydrogen here, you see that the difference in electronegativity is 2.5 minus 2.1, and that equals 0.4. Carbon-hydrogen bonds are nonpolar. And so if you see carbon-hydrogen, just know that's nonpolar. You don't even have to do this subtraction, but you can if it makes you feel more comfortable. And again, you will have this figure on any sort of assessment. So if we wanted to write the bond polarity, we use this lowercase d in Greek, the lowercase Greek d, so delta, and that's this letter here, and then we say delta minus or delta plus. And so here's another example. We have water, and we have our hydrogens and our oxygens here, and the electrons are pulled towards the oxygen, and the Pauling number here for oxygen, it's 3.5, and then hydrogen is 2.1. So this is quite polar, right? So 3.5 minus 2.1, we're talking about a difference of 1.4. So it is quite polar. And then we have the arrows pointing this way, so we're going to have this negative charge up here, so we say delta minus and delta plus. Now, it's not an ion, right? Because an ion is something like NaCl, and when NaCl dissolves, you have a positive sodium ion and a negative chloride ion. But water itself has that partial positive, partial negative. So let's do an example here that allows us to know if the compounds are nonpolar, polar, or ionic. So first off, we look at carbon-hydrogen, and we remember that the carbon-hydrogen bond is nonpolar, and if you want to use the Pauling numbers to demonstrate that, the Pauling number for carbon is 2.5, and for hydrogen it's 2.1. And so if we were to draw out our dot structure, we see that we have 3 hydrogens bound to this carbon here, and then that carbon is bound to an oxygen, and then there's another hydrogen. And so oxygen has a Pauling number of 3.5. And so if we look at this bond right here between the carbon and the oxygen, we can look at the polarity, and we can see that we have 3.5 minus 2.5, that equals 1, and then this one is 3.5 minus 2.1, which is 1.4. So there is going to be a significant partial negative on that oxygen, and so we would call this a polar molecule. Bromine, you don't even have to know what the Pauling number is for bromine because it's the same compound, right? And so if it's the same compound, there's no way for electrons to really feel any sort of pull in either direction. And so this would be nonpolar. So every molecule that is made of the same atom, so monoatomic molecules, those will be nonpolar. And finally, we have potassium chloride here. Potassium is a metal that makes a +1 charge, and chlorine is a nonmetal that makes a -1 charge. And so this would be an ionic compound. Our last example in determining solubility involves benzene as a solvent. And so benzene is only carbon and hydrogen. So remember that the carbon-hydrogen bond is nonpolar. And that means that it's only really going to dissolve things that are also nonpolar. So we know that this is a nonpolar bond, and if you wanted to double check with the Pauling numbers, again 2.5, 2.1, and that's 0.4, and so it is nonpolar. So now we get to decide if it will dissolve these. So first off, we have magnesium chloride. Magnesium chloride is an ionic compound because we know that magnesium is a metal that makes a 2+ charge, and chloride makes a 1- charge, and so it is an ionic compound, so it will not dissolve in benzene. Next, we have C6H14. This is a compound called hexane. It's a common additive to gasoline and a few other products, and it's a really common solvent that people use in labs. And if we see that it only contains carbon-hydrogen bonds, just like benzene, we can see that this is a nonpolar substance. And so that means that if it is nonpolar and benzene is nonpolar, it will dissolve. Finally, we have HCl. H and Cl, and I think chlorine's Pauling number is 3 and hydrogen's is 2.1. And so we get a 0.9. Chlorine is much more electronegative than hydrogen, and so it's going to have that dipole. It's going to have a partial negative and a partial positive, and since we have a pole, just like a battery, then that would make this polar. And so since HCl is a polar substance, that means that it will not dissolve. So now you have a good idea of how a solution forms and what a solution is, and you're ready to move on to doing calculations and thinking about concentration.